Participatory approaches in water management. This module introduces terms and concepts related to aquatic resources and their management. Various examples of participatory methods for water monitoring, assessment, governance, and conservation are highlighted and discussed. Within this module, you will learn about the water cycle and become familiar with key concepts and terminology related to water resource monitoring and management. You will also become acquainted with different use cases of participatory methods for water resource monitoring, and investigate different participatory approaches for water resource management and governance. Please familiarize yourself with the module structure. In this section you will learn about the water cycle, the different concepts and terminologies related to water resources, monitoring and management. Water covers approximately 70% of the Earth's surface. It exists in three physical states: in a liquid form, as a solid, such as ice, snow, or hail, and in a gas form, such as water vapor. Every molecule of water is in constant motion. The movement of water between the hydrosphere, atmosphere, soil, plants and other organisms is known as the water cycle. The water cycle is made of complex processes that help shape life on the planet. Let's define the key terms used to discuss the water cycle. Condensation is the transformation of water from gas to liquid or solid form. Clouds are water condensed. The opposite of condensation is vaporization or evaporation. Precipitation is the movement of water down to the surface of Earth either in solid, snow, hail, or liquid, rain, form. Evaporation is the movement of water to the air from sources such as soil, canopy interception, and water bodies. Transpiration is the movement of water within a plant and the subsequent loss of water as vapor through stomata in leaves. Evapotranspiration is the combination of evaporation and transpiration. Surface runoff is the flow of water over ground surface. This occurs when water cannot permeate fully through the surface as a result of saturated soil or impermeable paved surfaces. Groundwater recharge is water infiltrating soil and percolating through rocks to reach groundwater. Groundwater discharge is water movement from underground into surface water. If the majority of the planet is covered with water, why are we concerned about water scarcity? Despite the abundance of water on Earth, less than 3% of water is freshwater. The rest is characterized by high salinity, such as water in the ocean. Moreover, 3/4 of freshwater is trapped in ice caps and glaciers. Only about 0.5% of all the water on the planet is accessible for human use. Freshwater resources are not equally distributed worldwide. Parts of the world are rich in water, like the tropics, while other areas suffer from water scarcity, like the Sahara Desert. Not all available freshwater is clean and drinkable due to polluting activities. All these factors make freshwater a very valuable and scarce resource. Before we delve into freshwater scarcity and security, let's look into the different ways we consume freshwater. We use water for drinking, sanitation, recreation, all aspects of food production, such as agriculture, animal husbandry, aquaculture, fisheries, food processing and others. Water is used in the majority of industries, including mining, as a means of transportation for ships and boats, and as a resource for energy generation. The amount of water used within each sector varies greatly between countries. In low and middle income countries, the majority of freshwater is allocated to agriculture. Whereas, in high-income countries, a larger percentage of freshwater is used by industries. This is because low and middle-income countries often have a relatively less developed industrial sector and lack water-efficient irrigation methods in agriculture. Freshwater scarcity occurs when the demand for water from all sectors, agriculture, industry, municipal, and the environment, is greater than the available resource. Demographic growth and economic development are placing unprecedented pressures on water resources, rendering water scarcity to be one of the most serious contemporary challenges. Water stress refers to water scarcity, while taking into consideration water accessibility and quality. According to an OECD report on the environmental outlook for the year 2050, the number of people living near river basins under severe water stress will double between the years 2000 and 2050, reaching 3.9 billion people. Take a few minutes to complete these exercises. Explore the graph on global freshwater use during the past century. Describe the changes in global freshwater use. What conclusions can you derive? You can also download the data and explore it further by clicking on the link below the graph. Select your country and explore the changes of water use in the past decades. Describe the trend. Is it similar to the global trends seen in the graph on the right? What do you think drives these water use trends? Let's explore water resources in Armenia. Armenia is a landlocked country with no access to sea or ocean. Armenia's rivers are tributaries of the largest rivers of the South Caucasus, Oryx and Kura. About 9,500 small and medium rivers flow in Armenia, with a total length of 25,000 kilometers. The distribution of river flow in Armenia is highly uneven in terms of both annual and multi-year balance. The longest rivers are Arakelyan, 168 kilometers, Oryx, 158 kilometers, Vorotin, 119 kilometers, Debd, 154 kilometers, and Hrazdan, 141 kilometers. The average annual flow of surface water amounts to 6.8 billion cubic meters. The stock of groundwater resources is about 4 billion cubic meters. Armenia also has 100 small mountain lakes with a total volume of 0.8 cubic kilometers. The largest freshwater lake in Armenia and in the southern Caucasus is Lake Sevan. At an altitude of 1900 meters above sea level, it is one of the largest high-altitude freshwater lakes in the world, with a surface area of 1,279.5 square kilometers and a volume of about 38 cubic kilometers. The Lake Sevan Basin is a Ramsar-protected site due to its rich biodiversity and high degree of faunal and floral endemism. It used to be the home of the famous Sevan trout, Salmo ishchan, and is a breeding ground of the Armenian gull, Larus armenicus. On average, Armenia has a sufficient amount of water, with estimates ranging from 2,300 to 3,100 cubic meters per capita per year. These resources, however, are unevenly distributed within seasons and territory. The largest water-consuming sector in Armenia is agriculture with 88% of the total water use, followed by industry 8% and municipal use 6%. 96% of Armenia's drinking water is derived from groundwater, as well as nearly half of all abstracted water. The country has 87 single-purpose dams with a total capacity of 1.4 billion cubic meters. According to the Yale University's 2012 Environmental Performance Index, 70% of Armenia is under water stress despite receiving a significant amount of freshwater per year. The country lacks a systematic approach to managing its water resources and suffers from several issues. Most of the country's water infrastructure is in need of renovation. Leaks and losses within the system are widespread. Irrigation water accounting systems are inadequate. Wastewater is not fully treated, and in many regions, not at all treated. There are many cases of heavy metal water contamination by poorly regulated mine tailings. On several occasions, high contamination in transboundary rivers due to mining activities has caused disputes between neighboring countries, leading to international environmental courts and tribunals. This figure shows the amount of water loss during transit within each river basin area in Armenia. Overall, water loss in transit accounts for 40% of the total water use in the country. Climate change is projected to make water scarcity in the region more pronounced. Meteorological observations in Armenia were first conducted in 1929, and since then, the annual mean temperature has risen by 123 degrees Celsius. Mean air temperature is expected to rise by 1.6 degrees Celsius by the year 2040, and by 4.7 degrees Celsius by the year 2100. The calculations are relative to the baseline annual average of 5.5 degrees Celsius for the years 1961 to 1990. The average annual precipitation has decreased by 9% in the period from 1935 to 2016. A projected decrease of 2.7% and 8.3% will occur by the years 2040 and 2100, respectively. This is relative to the baseline annual average, 592 mm, for 1961 to 1990. Based on the worst scenario, a 39% decrease in the river flow is projected by the year 2100. What are the different traditions and use cases of water in your country? Think of ways to improve water use efficiency and to minimize water waste. What are the biggest water-related challenges in your country? Think of innovative solutions to alleviate problems. What opportunities can modern technologies provide? How will climate change impact water management in your country? How can we mitigate challenges posed by climate change? Please take a few minutes to explore these additional resources. In this section, you will become acquainted with different use cases of participatory methods for water resource monitoring. Public participation methods can be divided into two main categories: citizen science and co-design or co-creation methods. Citizen science methods are often used in research and data collection. Tools that include citizen science components are participatory sensing or mapping, open data collection and open voting practices. Co-design and co-creation methods are used to develop solutions for well-defined problems. Tools with such a component include open data initiatives, hackathons, gaming. In addition, workshops can also be used for both collective research and for co-creation. None of these methods are mutually exclusive. Many can be combined to meet the needs of different projects. For more information about participatory approaches, visit Module 1, Overview of Participatory Approaches. Participatory approaches are commonly used in ecosystem monitoring, including water monitoring. Water monitoring involves gathering rigorous, scientific data and information about water quality and quantity. The data is analyzed to determine whether water quality supports resource uses and whether the available quantity of water is sufficient to meet the needs of these uses. Data is also used to educate participants and to evaluate human impacts on water. Impact assessment of measures implemented to improve water quality are also conducted. Good water governance often entails effective monitoring of water quantity and quality. Participatory monitoring is the collection of measurements or data by local people. Participatory monitoring can be conducted as an alternative or in addition to professional scientist-executed monitoring. Involving local people and their communities contributes to the sense of sharing the management of land and the rights of the resources. Participatory monitoring can provide high-quality information, raise local awareness, and build community and local government expertise. It can also generate trust, help minimize or avoid conflict and enhance results. Participatory water monitoring is less costly and more sustainable, expedites data collection, while also capturing valuable local and traditional knowledge, helps raise awareness, creates a sense of ownership and adoption of responsibility by local communities, helps develop different expertise and facilitates an integrated management of water resources. Reduces or helps avoid water-related conflict by engaging citizens in decision-making process. The Secchi disc, created in 1865 by Angelo Secchi, is a plain white and black circular disc, 20 or 30 centimeters in diameter, used to measure water transparency in bodies of freshwater or marine water. It measures water transparency or clarity. In general, the higher the Secchi depth, the higher the water quality. Pollution and organic matter from soil erosion and excess nutrients from urban and agricultural areas lead to a diminished water quality, spread in harmful algal blooms, reduced freshwater ecosystem biodiversity, and depleted ecosystem services. Frequent Secchi depth measurements reveal changes in water quality over time and signal the need for intervention by a managing stakeholder. A comparison of water quality of different lakes within a region is also possible. The Secchi Disc campaign asks citizens to purchase or build Secchi discs, measure the Secchi depth of lakes or ponds, and share the data on a common platform. The project makes use of citizen science and open data practices. Interested individuals and parties use the online guidelines to monitor and analyze the water quality and submit the data to an open, freely accessible web platform. Thousands of Secchi depth measurements have been recorded and uploaded. In the first half of 2021, 10,589 entries were shared, bringing the total number of results in the databases to 128,715 entries. The data was analyzed and conclusions made. Follow the link to see the results. The project continues to improve scientists' understanding of lake dynamics and ensures the sustainability of the work. Case Study 2. Adaptive Management of Barriers in European Rivers, also known as AMBER. Dams aid in water abstraction for domestic and industrial use, help generate energy, facilitate navigation, and provide fishing and leisure opportunities. Increasing demands for hydropower and water abstraction leads to the construction of new dams, and the rehabilitation of old, abandoned weirs. All major rivers in Europe have been disconnected from the sea due to dams. The latest surveys have identified more than 1 million barriers in European rivers. This fragmentation has had a catastrophic impact on many species. The Horizon 2020 AMBER project was launched to reverse negative impacts and protect biodiversity in rivers through habitat connectivity. The project aims to map all European river barriers and evaluate the efforts of restoration actions through citizen science. The project engages stakeholders to employ adaptive management. The first task is to assess stream connectivity across Europe and highlight areas in need of restoration. A holistic framework of tools, models, and toolkits was then developed to guide the restoration of local river ecosystems and allow hydropower companies and river managers to maximize benefits and minimize ecological impacts. Citizen science is used to provide real-time monitoring to assess the effectiveness of the overall approach. Within the project, an atlas of all European river barriers was prepared. A holistic framework and tools were created to guide the restoration of local river ecosystems. Software and additional tools were developed to aid in river infrastructure planning, hydropower assessment, and simulation models. A citizen science app was developed to upload data and pictures of barriers. Case Study 3, Lake Sevan Hackathon. The water quality of Lake Sevan in Armenia has deteriorated over the past decades. Harmful algal blooms have started to threaten the lake's biodiversity and sustainability. Algal blooms are produced by the increased nitrogen and phosphorus concentrations in the lake. Due to financial and capacity limitations, in situ measurements of these parameters in Lake Sevan are sparse, amounting 6 to 7 measurements per year. The lack of data makes investigations into the drivers and impacts of eutrophication extremely difficult. To overcome the limitations of the lacking dataset, in situ measurements were complemented with freely available remote sensing tools. The American University of Armenia, in collaboration with the Ministry of Environment in Armenia and GIZ, organized a hackathon in 2021 to bring together multidisciplinary teams to develop algorithms that estimate the concentration of nutrients in the lake's water column from satellite imagery. More than 100 participants with various expertise, including natural science, biotechnology, machine learning, and data science, applied to participate in the hackathon. 10 teams spent 2 days on the shores of Lake Sevan to develop and test their approaches. Several teams developed preliminary tools to detect and estimate nutrient concentrations and submerged vegetation in Lake Sevan. The best 3 teams won financial incentives. The resulting ideas and work were handed to the Ministry of Environment for further development and integration in the monitoring of Lake Sevan. The event highlighted interesting interdisciplinary solutions to complex environmental problems and proved the effectiveness of knowledge integration through hackathons. Think of a water resource in your area. How can you contribute to its quantity and/or quality monitoring? Watch the video to explore other water monitoring methods. Case Study 4, Citizen Science for Community-Based Groundwater Monitoring. Monitoring of aquifer water levels supports sustainable management of groundwater and can indicate effects of water extraction, land use change and climate variability. These aquifers often have high spatial heterogeneity and require a large number of observation wells, a costly and labor-intensive undertaking. The goal of the Citizen Science for Community-Based Groundwater Monitoring project was to establish a large-scale water level monitoring network of private water supply wells in Alberta, Canada. The Citizen Science project aimed to highlight challenges and propose mitigation measures based on the collected data. The methodology used in this project can be adopted easily by other municipalities and watershed stewardship groups interested in groundwater monitoring. The community-based project involved university researchers, county staff and community volunteers. The volunteers were given monitoring kits, consisting of a water level sounder, spray bottles for bleach solution, clean water for sterilizing a probe, and latex gloves. Community volunteers measured the water levels of wells and entered the data on a web-based, freely accessible portal. Throughout the project, 39 volunteers measured and reported water levels of 39 wells every 2 months. The monitoring program was accompanied by education and outreach programs. Educational materials on groundwater, biannual newsletters and periodical surveys were developed in collaboration with volunteers and science teachers from local schools. The project developed a community-based groundwater monitoring network based on the citizen science approach in a large municipal district. It collected a large number of observation data of seasonal and inter-annual water level dynamics necessary to conduct analysis. The multi-stakeholder collaboration ensured the successful implementation and operation of the project. Explore additional resources on citizen science and public participation in water monitoring. In this section, we will investigate different participatory approaches for water resource management and governance. According to the UNDP Siwi Water Governance Facility, water governance refers to the political, social, economic and administrative systems that influence water use and management. In simpler terms, water governance influences who gets what water, when and how, and who has the right to water, their related services and benefits. It identifies the 4 pillars of water governance as social, the equitable distribution of water resources and services among various social and economic groups, and its effect on society. Apart from being unevenly distributed in time and space, water resources and services are also unevenly distributed among various socio-economic groups in both rural and urban settlements. Economic. Efficiency in water allocation and use and the role of water in overall economic growth. Effective poverty reduction and economic growth depend highly on water and other natural resources. The governance structures exert a powerful effect on per capita incomes in many countries. Political. Equal rights and opportunities for water stakeholders to take part in decision-making processes. Participation facilitates more informed decision-making, more effective implementation and enhances conflict resolution. A more effective involvement of commonly marginalized citizens, such as indigenous people or slum dwellers, and the recognition as legitimate stakeholders in water-related decision-making stands to greatly improve outcomes. Environmental. The sufficient flow of water of appropriate quality is critical to maintaining ecosystem functions and services. Unfortunately, water quality is declining in many regions due to insufficient safeguards by intensive agriculture and in large urban and industrial areas. For more information on water governance according to UNDP Siwi Water Governance Facility, visit the link. Integrated Water Resources Management (IWRM), defined by the Global Water Partnership, is a process which promotes the coordinated development and management of water, land and related resources to maximize economic and social welfare in an equitable manner without compromising the sustainability of vital ecosystems. To understand more about integrated water resource management, watch the following video. The IWRM principles adopted at the International Conference on Water and the Environment in Dublin, Ireland, in 1992, are known as the Dublin Principles. It states, fresh water is a finite and vulnerable resource, essential to sustain life, development and the environment. Water development and management should be based on a participatory approach, involving users, planners and policy makers at all levels. Women play a central part in the provision, management and safeguarding of water. Water has an economic value in all its competing uses and should be recognized as an economic good. Case Study 5. Restoration of Riparian Zones in Armenia. The restoration of riparian zones in Armenia COVID-19 response project was implemented in the framework of Green Recovery Initiative. The project offered temporary employment and income to individuals suffering from the socio-economic consequences of the COVID-19 pandemic. It simultaneously contributed to the restoration of the ecosystems of Lake Sevan and of rivers. German Corporation for International Cooperation or GIZ, jointly with the Ministry of Environment and the Ministry of Territorial Administration and Infrastructure. Local supporting partners included the Innovative Solutions for Sustainable Development of Communities ISSD NGO and Blegen Environmental, Social, Business Support NGO. Participants from communities were selected based on a COVID-19 impact assessment questionnaire. More than 200 participants received training on recycling and more than 500 participants received willow planting training. From May 3 to May 11 of 2021, 135,990 willow cuttings were planted in the riparian zones of Masrik and Karchabir rivers in the administrative areas of Metz Masrik, Okpradzer, and Vardinas communities. Overall, 63 people from these communities took part in the planting activity. From October 13 to 17 of 2021. Cleanup activities took place in Noradis, Martuni and Engedishan communities along the Gavrije, Martuni and Argishti rivers. 100 participants were involved in the cleanup activities. In all, 54,577 kg of trash and 356 kg of recyclable waste were collected. From October 21 to 25 of 2021, cleanup activities also took place in Gavar, Ganzik and Sovajiug communities along the Gavrije and Desnajay rivers. 86 participants were involved in the cleanup activities. In total, 42,566 kg of trash and 218 kg of recyclable waste were collected. Case Study 6. Stakeholder Consultation within the River Basic Management. River Basin Management Plan (RBMP) uses economic, social and ecological aspects of a specific river basin in the development of sustainable water management measures, strategies and policies. RBMPs are developed using a participative approach. Multiple stakeholders with various viewpoints are included in basin council meetings, stakeholder meetings and public consultations to determine how water should best be managed. According to EU Water Framework Directive requirements, all stakeholders, including NGOs, local communities and water supply enterprises, should be involved in discussions leading to the formulation of the River Basin Management Plan, to inform all interested parties about possible issues related to the river basin, collect information about demands and issues at a local level, explain the various alternatives and reach a consensus between the authorities and stakeholders. For more information on the guidelines and mechanisms of involving the public in river basin planning by EUWFD, visit the link. Stakeholder consultations on the Sevan Basin Management Plan were conducted in Gohar, Armenia. Representatives of beneficiary institutions, regional and local authorities, and NGOs gathered to discuss the main issues of water management in the basin and indicate measures to address issues. Stakeholders were divided into 3 groups and were provided a watershed map with settlements and water objects. Participants with different expertise and backgrounds, including representatives of local and national authorities, water resource experts, NGO representatives and/or active citizens formed groups. Participants were given 30 minutes to identify and describe the main sources of pollution and areas with water issues, including overexploitation, using local knowledge, experience, and by analyzing the information presented in the draft Sevan Basin Management Plan. They were also asked to propose measures to overcome these problems. Pollution hotspots, intensive water abstraction points, active agricultural and tourism zones, and other relevant sources were identified on the map. Maps were presented and solutions recommended, including building a wastewater treatment plant, introducing water-saving technologies, and organizing awareness-raising campaigns. To ensure the maximum engagement of stakeholders in the participatory process, an online questionnaire was also developed and distributed within different stakeholder groups. The participants identified prominent issues of water usage and pollution, and discussed treatment and allocation of water resources to ensure fair and sustainable use. Results were considered during the development of the final version of RBMP. Watch the following videos to learn more about integrated water resource management, participatory water management, participatory modeling. This module is developed in the frames of the German-Armenian Network on the Advancement of Public Participation GIS for Ecosystem Services as a means for biodiversity conservation and sustainable development, also known as GATES. Financed through DAAD, the German Academic Exchange Service, with funds from the German Federal Ministry of Economic Cooperation and Development.